Hey, everyone. So yeah, you were probably expecting to see this, but as you may have guessed, I'm not Jeff. I'm actually this guy. So this talk isn't really about that. It's actually going to be this, indexing thousands of writes per second with Redis. So my first question actually is, who saw this talk already at RailsConf? Okay. I'm very sorry. I probably bored you then. I would like to say I'm going to blow your minds right now, but you'll probably be bored now. Just stay here for the comedy, maybe. All right, but I have bonus material maybe if I can get to it. If I can like just jet through these slides really quick, then I have something else I want to talk to you about. Amway. So first I want to say how happy I am to be back at GORUCO. The organizers, I mean, I figured there was no way in hell I was going to get to talk here again because I've already spoken here a number of times, so it's like, who wants the Paul Dix show? But guess what? So here's a little bit about me. I live here in New York. I wrote this book with some other awesome people who are in the audience. I work at this company, which is a data company. Now, before we actually get to the talk, I know it's like more leading up, but who went to the Pivotal party last night? All right. Woo, Pivotal! All right. So some of you may have heard this nasty rumor. You know, a couple of people were talking about it. You know, obviously, some people were excited. Now, what that was about was a bet. Now, like all great or stupid bets, it begins in a bar. And I was hanging out with this guy, with Mike D'Alessio, and I was saying how awesome JSON is versus XML. Like XML is like weak sauce, and JSON is like the best thing ever made. I mean, the parsing is so slow. In fact, I said it was like 10 times slower. Now, Mike, being an XML guy, called BS.
Was he more sober than you?
Yes, but he has a few pounds on me, so I'm a lightweight. I'm a cheap date. So basically, this was the bet. Let's make it interesting. The loser of the bet has to wear his daughter's fairy wings during my talk at RailsConf. That was not here. So at the time, I thought, hell yeah, that'll be funny. And then I saw this. Dr. Nick already did it. What the hell? That's BS. So who won, you might ask? Now, since I don't have wings, John Berger has thankfully supplied us with an artist's conception of what would happen right now. So this is it. These are all the wings you're going to get. Blame Mike for not stealing his daughter's fairy wings and bringing them to the conference. It would have been even better because once we got on the boat, somebody would have gotten drunk and they would have been flapping around like a fairy. You missed that. So the end result was that Nokogiri was about 6.8 times slower. RexML was insanely slow. The lesson there is to always use JSON. And also, don't make bar bets. But the thing about this bet is that it said nothing about my slides. And for those of you who saw Aaron's talk at RailsConf and saw the RailsConf website, this was the picture that he used for his headshot, which is completely awesome. Anyway, he called himself the father of Nokogiri at RubyConf last year, and he called Mike Nokogiri's mother. So for the purposes of these slides, I figured, well, why not a fairy godmother? Another lesson, I really, really can't use Photoshop at all. So actually, I'm not wearing the full suit. I'm only wearing the jacket, as you can see. But the point of it is that you take me seriously. So, all right, sorry. We're gonna go to the talk now. So it's about Redis, and it's about how we used Redis at work to deal with the sustained write load of about 5,000 writes per second. And it you know, ebbs and flows, but Really, like, that's all the time. And how we used Redis along with another data store to do some awesome stuff. And maybe about Mike as a virgin mother. So yeah, another lesson. So who here has actually used Redis? Who here has used Redis but not for rescue? Okay, I see. All right, so let's get through a couple of basics for the other people in the room who aren't lucky enough to know about it yet or how awesome it is. So it's a NoSQL data store. Some people know it as a key value store. It's created by this guy who works here. But it's more of a data structure store. So here are the basics. You have keys, you can get, you can set, you have counters, you can increment, you can decrement, you can increment by a certain amount or decrement by a certain amount. Hopefully I'll retain a little bit of dignity before this is done. But you can expire keys in a number of seconds, or you can expire them at a specific time. Hashes. So hashes are you have a key, and then you have a field name, and then a value for that field. So you can set them, you can get them, you can multi-set and multi-get. Lists. Lists, you can, again, it's just like an ordered list of things. You can push on the left, you can pop on the left, you can push on the right, pop on the right. And they're actually pretty useful for doing things like queues. Sets. So a set is where each member is unique. So you can add things to a set. You can see how many members are in the set. You can check to see if something is a member. And these operations are all very, very fast. So a few of the other interesting things about sets is that you can do intersection with them to see which members they have in common. You can do differences between them, or you can do unions. Sorted sets are just like sets, except for they had another component, which is you have a sort key that you can store things under. So again, adding, checking the size, seeing if something is a member, and you can pull back ranges of the sets. So here we can see pulling back a range, getting, in this case, 0 to -1, which means we're getting everything back, where 0 is an index and -1 is just the end of it. So you can also pull back by score. So essentially, the score is the sort key that you're using. So it's assumed to be a string that's interpreted as a double value. If we want to pull back everything, we just say we're pulling back positive infinity to negative infinity. And here you see I'm doing like z rev range. So rev is to reverse the order. By default, the order of a sorted set is ascending. So in this case, we're saying reverse it, so we're getting stuff in descending order. I don't know if any of you were reading the text there, but I was trying to do this whole, like, Mike is a fairy godmother and he's granting wishes, and yeah, it just didn't. I don't think it quite worked as well as I would have liked. So there's more that Redis can do. It's insanely fast, like crazy fast. I mean, this fast. So some of you may be thinking, like, it's so fast, it's the answer to all my prayers. Like, I can scale infinitely with it. But no. There are some limitations. But first, another lesson for you. It's still a monolithic data store. It still exists on a single machine and actually in a single thread. So if you want to take advantage of a multi-core box, you have to run, and you're CPU bound on your Redis instance, you have to run multiple instances of it. Now you can get around the fact that it's monolithic by doing sharding, like in a Memcache client, and the Ruby client actually has that built in, which is nice. But also it's still not highly available. If your Redis system goes down, like, all that stuff is gone until you get it back up. Or if you have a slave, you still have to have like this manual failover process where you connect to the slave, you promote it to master, and then you have to like try and sort that all out later, like when you get the old master back up. It's susceptible to network partitions. If you have a bunch of Redis instances, like say you have like 5 instances that you have in your cluster, and you have data spread out across all of them, if the network goes down between your Redis, one of those instances, and your, wherever it is you're accessing them, all that data that was storing is gone. So, I mean, it's good because you still have at least 4/5 of your data, but there's a chunk that you don't have of access to. So with all that being said, I still think it's a really awesome tool. Now, one of the questions you may have been asking yourself when you first saw the title of this talk is, why in the hell would you want to index with Redis? Like, databases do this stuff already. And I'd say, you're right, don't do it. It's kind of silly. But at the same time, you may be saying, I have to scale. No, you don't. Use your database a little bit more wisely. But actually, sometimes your database really is just buckling under the pressure, and it can't deal with the amount of things that you're throwing at it. And in that case, I would say fine. So that's what happened with us. Now, we're a little special because we don't have a ton of unique things coming into our system. It's more like 40,000 things or somewhere around there. Like, actually, I'll probably double that by now. But they're the same things. They're just being updated all the time. They're updating every 10 seconds on average. And there are a bunch of other updates. But all those are associated to these like 40,000 unique things that we're tracking. And all of that adds up to about 3,000 to 5,000 writes per second. So with us, we have like this data store that can keep up with that. It can take all that data, but it isn't good at answering certain queries that the users have. So the first thing we had to do is we had to create a last value cache, which we used Redis for. Because amazingly enough, this data store couldn't answer the simple question of, for this thing, what was the last value that you saw? So what we used for this was we used hashes where we said, OK, in this case, it's bonds that we're storing. The ID is 1. And the field that we're storing is the bid price or the ask price. So there you can say, like, we're setting those. And the other thing we did is for everything that we're tracking, we're adding its ID to a set. And we'll use that later. So what that does, like that structure, that simple structure, lets us kind of index on the fly using the sort command. So if we want to get an ordered list of, say, all the bonds we have in our system by the bid price, we can just say sort this set, so the set of IDs, by this hash value. And the asterisk there at the top, it knows, like, it'll go through the set and replace the asterisk with the specific ID of each one. And it'll return back those IDs. You can also, in that case, it returns the IDs, which is great, but say we also want to get like the prices. Or we can get both. So the other nice thing about sorting is it has built-in tools for doing pagination. Obviously, like if you have 40,000 things, you're never going to show that on a single page. The user's only going to want to see like a certain chunk of those. So that's where a limit comes in. And the first is the offset, and the second is the number of items that you're returning. So it's like a page per page kind of thing. You can also change the order it by descending. By default, it's ascending, just like sorted sets. One other thing you can do, we actually don't do this because for us, it's fast enough to just do everything on the fly. And the thing is, like, when users are making this request, they're going to be requesting from their browser, like, every 10 seconds as well, and it's still like crazy fast. But if you have a much bigger set, which might be the case, you can actually store the result of the sort. So for us, we can't really store results because we have everything updating so quickly, but a lot of times if you want to cache that sorted result, you just say store it in this set, and then you can, other people making that same request can come in and pull that out without having to like recalculate the whole thing. So if you're using Redis in addition to like, you know, another data store, you're going to have to get back the records once you get that sorted list of IDs. Now, here in this example, we're saying, OK, we have this model called bond. We're going to call find. And it's a little kind of convoluted because if you do find and you pass an array of IDs, it doesn't actually preserve the order of those IDs. So we're going to loop through those bonds and just create like a hash that maps the ID to the bond itself. And then we're going to loop through the actual ordered array of IDs, which is the results, or the actual IDs, and then just look up those bonds out of that in-memory hash. And that's fairly quick. So you can also actually just store the values in Redis, which is what we're doing. So we have that hash where we have like the bid price and the ask price, and then we also have this member called values, which is just JSON of the entire data object. So we pull that out. And the reason we do that is because we have like crazy servers with like 65 gigs of memory, and we can do that. But if you don't want to do that, you can keep it in the data store. So the other example is pre-indexing, and we're using this as well. So this is something I'm calling a rolling index, which is really good if you want to like look up and store like the last n events. A typical use case would be like an activity log or a news feed for a social network or something like that. So one way you could do it is to use a list. So we're going to say we care about the last 500 things that happened. So we're going to just say push this item onto the list. And in this case, we're saying, OK, we're storing like trades. But let's do a social network example, like we're storing a comment or something. And the result of the push is actually the size of the list. And then what we do is we just pop off the right-hand side if it's bigger than we want to keep. And the reason we're doing this is just to keep the memory footprint small. And the other thing is you should, when you're doing things like indexing or like you have these sorted result sets, it's good to think about how many results you actually care about returning. You know, like you go to Google and you do a search and they say like, oh, 20 billion results, and you have pages and pages of stuff. But the truth is like nobody ever gets past like page 2 or 3. So if you don't need all 100 million records or whatever that you're keeping to show up, just keep like what you're interested in, which is what the user would probably look at. So our example is indexing events since time t. Obviously, because we're storing financial data and we have like all these ticks coming in, these like information about transactions coming in. So we care about all these things since a certain time. So you can use a list for that as well. In this case, you have the key of the list contain the time bucket that you're interested in. So basically, you just create like these buckets of time. And you could create it as a year, a month, a day, or an hour, or a specific time frame. So in this example, we're saying, you know, the 19th of May, the 10th hour of the day. And we're just going to keep a list, and that's going to keep all the trades that happen during that 10th hour. And we're also going to keep it limited. And if we want to actually pull back, like the trades for 2 hours in a row, you can use this pipelined approach, which is actually, the nice thing about pipelined is it'll make only one network request for all the commands that it's executing and just return the entire result set to you. So here we're saying, let's get the trades for the 10th day, or the 10th hour and the 9th hour, and pair them together. And the nice thing about this is that they're actually already ordered in the way we want, because the way we were pushing onto the list. So rolling the index when you have like time buckets is a little bit more complicated than just the simple list rolling example. So we keep adding things. What we're going to do is we're going to have a set in Redis where we say, for this time bucket, these are the items which had like activity. These are the bonds that had activity. So that way, we can have a cron task that'll go through and clean all that stuff up later. So we're just going to say, let's look at the traded IDs. Let's get all the members of the set. And let's create the set of keys that we actually know we want to just go through and delete. And then go through and delete those. The other thing we could actually do is use expiration, which I don't know why I didn't in this example, but you could do that too. So sorted sets. You can store time, you can keep rolling indexes in a sorted set as well. And these actually work well for time if you use just the like epoch time as the sort key. So here, again, we have a trade. We're storing it. If we want to pull back the last 20 trades that occurred, we just access using zrev range 0 to 20. Reverse, again, because they're in ascending by default, and we actually want them in descending because it's a time. And finally, we can actually just say, oh, what are the trades in the last hour? We can pull them back by score. So rolling that index, again, create a cron task to roll it, and basically you just want to say, like, how big of a window of time do we care about? So let's say we want to keep everything from the last 24 hours. We just execute these commands to clear out the members of each of those sorted sets whenever we run this task. So the other option with the sorted set is we could actually roll it over on the read or the write of the set. So here we're adding a trade, and then at that point we just call the remove of the range right there. So we just continually remove it. It adds an extra operation, but it just makes sure that it makes it so that we don't have to have that separate cron tab and keeping track of everything. So another example is indexing n number of values. So the time one was we're using the time as the key. In this case, we're just using the count of something. So like I said before, the sort key is really just a string that can be interpreted as a double precision value. So with this example, say we want to keep the highest follower counts and the lowest follower counts. We don't care about the middle of the pack because nobody is ever going to look there, right? So we just want to say who are the people who have the most followers and who are the people who have the least followers. So whenever a follower gets added or removed, we update highest follower counts with the number of followers and where 20 is the ID. So now we roll the index, we keep the lowest by checking the size of the sorted set and then removing that range, removing the set that we don't care about. And here we can see on the lowest follower counts, we're removing from n, where n is the number, say it's 500, to the end of the set, because again, it's ascending, so lowest are going to be first. And the highest ones, we actually have to flip that on its head. We're removing from the 0 index up to the size of the set minus n. So one of the things is that this kind of approach takes a couple of round trips to your server, which can take extra time, even though Redis is crazy fast. And even to do it in only 2 round trips would take a really complex bit of pipelining code to actually do it. So it is possible to roll indexes with only 1 trip. And that's going to be when the scripting branch gets merged into master. So what the scripting branch is Salvatore worked on giving Redis server-side scripting so that you could actually write Lua scripts and send them to Redis and do things like get certain things, check values, and modify some other things based on those values. Because what he found was that majority of the CPU time in Redis is simply from parsing the commands, parsing the network commands, as opposed to actually doing things like sorting on the server or keeping sorted sets in order or anything like that. So obviously, since we have Redis as a store and it's not like the canonical data store, we have a separate data store that's actually storing all the real data. We need to make sure we keep it consistent with our primary data store. So we can do that through normal methods of saying, oh, on create, update, destroy, update these things. But the problem is it's a separate data store. So we don't have that in transactions. We have to put it in application logic. So we need to make a plan for disaster recovery. And 2 of the failure scenarios that I thought about were, 1, what happens when the web app dies? So basically, you write a record to the database, and then the web app dies before it writes the index update to Redis. And then the other is what happens when the Redis server dies. And this could be a couple of things. Either the same case, the web app writes the record to the database, but it doesn't write to Redis. Or depending on how you have Redis configured, you may actually lose a couple of seconds or whatever worth of data. So essentially, that's going to result in an inconsistency in your Redis index versus what you have in your data store. So you can actually cover these cases with a simple recovery script. So here we're going to say we're just going to write the index times. So we're going to say the last bond trade that we indexed was at X time, right? And this is just going to be a single key that we just keep updating to every time we perform a write on the index. And then if it fails, then we just need to write a script that looks at that time, gets it out, and then does a lookup on the database, loops through everything that happened since that time, and updates the index. So our scale, like I said, we're doing like 5,000 writes a second, which is certainly like some of the heaviest write load I've ever had to deal with. Some of you might think that's kind of weak, but it's all happening in a single process, actually a single thread. We have one Redis instance running, we're not splitting anything out, and it's not even near CPU bound, and we still have a good amount of memory left. But the thing is, the way we've designed it is it's easy to scale. We can actually separate these different indexes off onto separate machines without too much difficulty. And it's been working really, really well. So some final thoughts on the indexing stuff. I would say use it only if you really, really have to. Adding another data store that you have to keep consistent with your primary data store, it's just like a lot of complexity. Really only index the minimum that you need to keep around. Your users aren't going to look at 20,000 different records. Don't worry about keeping 20,000 records. Just worry about keeping the set available that they care about. And finally, plan for disaster recovery and consistency checking on your system. So it looks like I have a decent amount of time left. Yes, nice. OK, so now this is like the whole bait and switch thing. That actually took longer at RailsConf because I was like clowning around more, maybe? I have no idea. But so you RailsConf people who already saw this, you can look away from your laptops now and gaze upon me again. So this is the bonus material, which I just kind of hacked together last night. But it's something that I've been playing around with recently, and I'm going to be working with, I think, a lot more in the coming month, which is really ZeroMQ. So ZeroMQ is kind of like a network library, right? Like it's not a queuing system like RabbitMQ or ActiveMQ or Rescue. It's just like a really easy to use network library, but it's really fast. It's awesome. It's sockets programming that isn't completely shitty. So here's a small example of what a client in ZeroMQ might look like. So again, like this is just like different servers talking to each other. So this client says, I'm just going to create this context, connect to socket. ZMQ rec is a specific type of socket where it's going to be making requests. So we're going to call this a client. We're going to connect it. Now, the nice thing about the connect call is that it doesn't throw an exception or die if the server doesn't happen to be up yet. Like, you don't have to worry about, oh, I'm going to start the server, and then I'm going to start the client, and then everything's good. It actually just works. So here, again, like really simple example is just like sending a bunch of messages over there. And then getting back a response. So this is actually a synchronous example. This is what the other side of that might look like. So basically, you connect to a broker in the middle, and the client connects to that, and then the service connects to this guy. The broker doesn't keep anything. He's just responsible for routing messages between the two. Again, it's really, really simple. You create the context, create the socket. In this case, actually, that should be a rep. That's what happens when you write code the night before at like 12. And then connects, and then it just like continually loops. And again, this is like, it's really this simple. Like the do something awesome thing is where you would obviously like call out to some model, but the entire server is contained in these few lines of code. There's no additional thing you have to run. It's not like, oh, like a REST server where I have to run like Apache and all this other stuff. Like you can just no-hup this guy and go away, and it'll run. ZeroMQ also has built-in functionality for doing async stuff. So those two examples were synchronous, which means it's going to send it out and wait for a response. The async stuff is, I'm just going to send a bunch of things out and let the operating system deal with how to optimize sending that over the network, and I'm not going to block the thread that I'm in based on that. So Node fans are obviously familiar. with that, or event machine fans. So the reason why I'm kind of psyched about ZeroMQ, other than the fact that it's awesome and fast, is that I've been seriously considering it as a messaging bus for internal services. Internal services meaning like I have different systems communicating, but nobody from the outside is coming in. So I really think that REST is ill-suited for internal services. I know this is like heresy being that I wrote a book on this stupid stuff, but so I'm kind of like backtracking on that, but so the rest of this is kind of like a design discussion, because what I really want to do is I want to create like an open source like messaging bus that's scalable, that doesn't rely on HTTP. It relies on something much simpler and that works really quickly. Unfortunately, there's no code because, like I said, this is a design discussion. You can all like help me out. Like I'm going to vet this with you, and you can tell me how stupid I am because there's something like this that already exists. So my goals here are that I want something that's highly available. If I have a messaging bus that I'm connecting to and one of the systems fails, I want it to be very, very simple to reconnect and keep sending messages. And I also want it to be simple to make sure that I didn't lose anything. I want it to be scalable. If I need to scale up to sending 1 million messages a second, I want it to be able to handle that. If I need to scale up to running 200 different services, I want it to scale to that as well. So it consists primarily of 3 components. There are clients or publishers. So the clients would be, say, in your Rails app, when you receive a request and you're going to call out to a service to perform something. That's a client. Or a publisher is going to be like, if you have a background process that's, say, listening to Twitter activity and it's writing that data, it would just publish that Twitter activity internally, right? There's the routing network, which is the back-end thing. And I'll talk about that in a second. And then finally, there's the consumers and the services. So the services are, say I have like a user service that is just responsible for storing user data, and that's what it does. So that's a service. A consumer would be something more like, say I'm writing instrumentation information. That's publishing, right? Because I don't really care about the reply. I just want to send it out into the ether so that somebody can deal with it. So I would maybe want to have a couple of different consumers on this. I'd have one consumer that would just take all that data and write it to disk somewhere, or write it to somewhere where I can do analysis on it later. And then I might also want another consumer that does real-time analysis so they can send a text message and wake somebody up if something bad happened, or it can do any other, like it can contain any other kind of logic. So here's what the routing thing kind of looks like. So the idea is I have a bunch of different routers, anywhere from 1 to however many. And the routers all talk to each other. They're like lunching ladies on the Upper East Side. They gossip a lot. And they tell each other about, one, like what their utilization is, how much memory, how much CPU, how many messages a second they're getting. And they also tell each other about the publishers that they're publishing that they know about and the clients they're consuming. So the publisher protocol would look something like this. Say we have this activity service, and it's going to be making requests for activities or publishing activities or whatever. So the first thing it's going to do is it's going to connect to a router and say, hey, I'm publishing this stuff. And the router is going to respond back and say, hey, I either know about clients that are connected to other routers, and I will just send you to those routers, or I don't know about anybody yet, but here are the 2 routers that are the least utilized in the network right now. So it's going to reconnect to those 2 routers. And in this case, I say 2 because, again, I want it to be highly available. If one of these routers fails, I want there to still be another route to publish messages. So the other side of this is the consumer side. Again, he's going to connect to any router in the network. It doesn't matter which. He's going to say, hey, I'm interested in activity service, or I can serve activity service. It's going to get a response back that says, oh, I know about the activity service. It's getting published to these 2 routers right here. So it's going to connect to both of those. And essentially, whenever the activity service makes a request, it's going to round robin between the 2 routers. And that's just going to go back to the service. It's going to craft a response and send it back, and that's going to get routed back. Now, the routers themselves don't carry any state other than what publishers exist and what consumers exist and what the utilization is for the other things. They don't keep the messages in memory, so there's no chance of having a consumer getting backed up and having it overflow the memory on the router. So the underlying mechanism is whenever the activity service sends a request, it just attaches an ID to it so that the router just forwards that along to the consumer sends it back, and the router knows where to send it because all the routing information travels with the message each step of the way. So here's what that looks like if we have multiple consumers. So say like one consumer starts getting overloaded, so we're gonna add another consumer so that we can scale up. And in this case, again, like the message will go to, say, it'll go from activity service to router 2, and then router 2 will round robin between the two different consumers that are capable of handling it. If any consumer fails, you're still up. If any router fails, you're still up. And here it is, like with another service added in. And here we see it connected to different routers, and then the consumer connected directly to those routers. So the responses can be guaranteed, again, because if you attach like the design I'm thinking of is if you attach hey, I want a response to this, you have to attach like an ID. Then the service, when it gets it, knows I have to send a response. Otherwise, it can just like disappear. So you can get guaranteed delivery. Ordered delivery is something that I'm not sure I'm going to add in. It depends on whether or not it's important. It's that question of FIFO. Do you really need it? So some possible code just on the publisher and the consumer side, because the router side would just be like, you wouldn't have to worry about that. That is my unfortunate task. So it looks something like this. Like say we're gonna create a new service. It's gonna connect to those two routers. The negotiation between what routers it reconnects to happens automatically in the background. The async example would be you publish some activity and you publish either some JSON or protocol buffers or whatever it is that you want to use as your serialization, maybe even XML. But I won't talk to you if you do. And the synchronous version is just like calling a method. So the example of the service or the consumer is very simple. You create that, you connect, it does the reconnect, and you just say on request, do something. I think it's really simple. So I'd really be interested to hear people's thoughts on this. I am also going to be on the boat, so don't throw me overboard, talk to me. I'm also taking name suggestions for whatever this thing is going to be called. All right, thanks. Huh? All right, questions?
Fairy wings, fairy wings.
Fairy wings? Oh, yeah. Mike did not steal them from his daughter. Yeah.
No, that's what you have to call it.
Oh, I'm going to call it fairy wings? Oh. I didn't even pick up on that. I guess I could. The question was, do I have any plans for UDP support, or is it just TCP? I hadn't thought that far along about it. I guess I could. So the question is, what are the latency properties of doing something like this? It really depends on how fast your services respond. If they respond quickly, then the latency is, whatever the network latency is. I mean, it can be extremely low, like sub-millisecond. The question was, does it use any bit packing to like consume less network? My intention was just, there's going to be a string. I don't care what it is. So if you want to wrap it up and like gzip it or whatever, like go for it. But yeah. Any other questions? Yeah. The statement was, there are a lot of message queues out there. Is there something I'm looking for in particular that I'm not getting? How am I not being satisfied? So I used to be a very big RabbitMQ fan, and I still think RabbitMQ is pretty awesome. But their solutions for high availability is non-existent. They tell you run HA Linux or duplicate your messages across different servers, which is profoundly unsatisfying. Like, I can get high availability in my data store if I use React and Cassandra. Why can't I get it in my messaging system? And the other thing about Rabbit is that a queue, the throughput of a queue is limited to a single box and actually a single thread. Because when you create a queue in Rabbit, it lives on one place. And if you overload, like Tom was saying, like you overload what that can handle, your only recourse is to create a separate queue and start sharding across the queues, in which case you've leaked your scalability solution into your application logic, which just makes me very, very sad. And I haven't found, so the closest thing I found actually to being a highly scalable messaging system is a system that LinkedIn developed called Kafka. It looks very interesting. You should read the paper on it, the write-up they did on it, because they have like a bunch of cool numbers in there and about how like you can actually spool to disk faster than you think you can, so don't be afraid. But the one problem with Kafka is you have a single point of failure in a broker. If a broker fails and there were messages on that broker that hadn't yet been delivered, you won't get those messages again until the broker actually comes back up. So I guess I'm not finding the combination of high availability and scalability that I really want. And I want something that has a more flexible architecture. I don't want something that says, like, I have an architecture that looks exactly like this, and I'm going to construct these things. I want something where I can just have like EC2 instances that are coming up and down and can get added to the architecture on an as-needed basis. I know, so this is like, I'm going to end this with a total cliche. I want a messaging system that's designed for the cloud.
Thank you for that cliche, Paul. Ready for your talk.